I'm happy to take more advanced questions as we go, but obviously we'll have to stay on track. This is a 50-minute presentation. I would normally do this course as a 3-day course, okay? So, there's a fair bit of detail, but I can, this is like an overview, right? So the good bits, okay? So who am I? I'm Simon Riggs. I'm the CTO of Second Quadrant, a leading Postgres support company. I'm a database architect as well as a developer. And I've been a Postgres contributor for 15 years. And one of the areas of Postgres that I've developed has been a lot of the features that I'm going to talk about here today. So even though I'm giving an overview, I do know exactly what I'm talking about with regard to some of these features. So the topics I'm going to talk about are, first of all, replication for high availability, and then I'm going to talk about the wider subject of interoperability and remote data access, and then I'm going to talk about more complex architectures, multi-node databases to end up. Obviously, with 50 minutes, I'm going to breeze through some of these subjects like they were quite short, and obviously there's a lot of detail there. So, replication for high availability is the first topic that I'm going to talk about. And just to explain that this is in many ways similar conceptually to the way MySQL works in terms of high availability, but actually the under the cover details are quite different in various ways. So Postgres supports what we call physical streaming replication. Now it's called physical replication because we are sending the transaction log directly to the second or multiple other nodes. So physical means if we make a change to an index or we do some maintenance work, that gets reflected in the transaction log and that gets sent as well. So there's been some differences discussed with respect to MySQL, where MySQL sends the logical changes in the bin log. We do also support something called logical replication, which is much more similar to MySQL replication, and that's why we use the terms logical and physical. So physical is sending the exact transaction log onto subsequent servers. We use the term streaming because that's done in real time. So if you've got a long transaction, we start sending the transaction log before the transaction's even committed. So the end result of that is if you run a very long transaction and then abort that transaction, we've sent virtually all of the transaction log data with that abort as well. Now that sounds like a downside, but it's actually an important distinction in terms of latency, because it means that when it comes to committing a transaction, the only thing remaining to send with physical replication is the commit record itself. And what that means is the latency for physical streaming replication is extremely low, and that's one of the properties that makes it very suitable for high availability. So we support streaming to multiple nodes at the same time in separate processes, so they're completely concurrent, and we support asynchronous and synchronous replication, which in the MySQL world I believe is called semi-synchronous replication, very similar. We do also support two-phase commit, but we don't really regard that as a form of replication, so forgive me if I don't discuss that much here. There's quite a few other features to talk about in terms of replication. You'll see the diagram on the right shows that we send data to one node and then we're able to send that to a subsequent node, and that's what we call cascading, and that allows us to assemble quite complex architectures of interacting nodes. The other thing to say is that you can actually execute read queries on the standby nodes, and that's what we call hot standby, though Amazon have chosen to call that a read replica, which is in many ways a good way of describing it as well. So we use both terms really, the hot standby or a read replica. And on the left, you can see one thing that people do frequently, which is to use both the cascading feature and the read replica feature to create a server farm that can allow you to do read scalability on your applications. Now these technologies have been around now for nearly 8 years, so they're very heavily used in the Postgres world, and they're obviously quite robust and advanced in the way that they operate now. So we've covered off lots of different bugs, lots of different usage angles. One of the things when MySQL and Postgres started some years ago, was talking about usability, and we've spent a long time now making these things really quite usable. So it's a small number of commands to get these things to work, and it's fully integrated into the core server, so you don't need to install 7 other pieces of software to get it to work. Summary of that is that the streaming replication is done using the write-ahead log or WAL data, and there's a couple of other tools that you might want to use for management of clusters. Second Quadrant produced something called Rep Manager, though there are other ways of managing a cluster's failover capabilities. And there's also another tool called Second Quadrant Barman that does backup and recovery management. But again, there are other tools that you can use for that as well, many of them open source. And obviously, if you're in the cloud, some of these things will be built into the service that you receive from your vendor. So that's just really a short summary of the high availability technologies that we have within Postgres. What I'd like to do now is move on to describe remote data access techniques that we use within Postgres. Were there any questions about that before I move on?
Were your 2 solutions open source or no?
Rep Manager and Barman, yes.
Open source?
Yes. I believe they're packaged for Debian and available on multiple platforms, that kind of thing. So again, both of those have been available for quite a few years. Yep.
So is your physical replica open and it's available for read and updated consistently so it can change with the privacy?
Yeah, that's correct. It's updated in real time, and the visibility mechanisms that we use to see data that's already existing but not see new transactions it exists just the same on the read replica, so you get fully consistent answers to queries running on those servers.
So on the standby side, read and write standard block in sharding.
Sorry, could you say that again?
On the read replicator side, it's a physical standby. So read and write can happen at the same time.
Yes, that's correct. So the read queries do not block application of new changes from the master, and those changes are applied in real time. Obviously, there are some cases where the incoming write transaction would need to write to a data block, and that momentarily would block the reading of that data block. But those are sort of instantaneous resource contention things rather than actual data locks that prevent queries. So this all happens in real time. Yep. Well, I was just explaining that you could replicate across regions. The example here, cascading, shows that if you were replicating from the US to Europe, for example, you would use the cascading feature to avoid sending the data twice to those nodes. So it's a way of bandwidth reduction as well as a way of assembling complex architectures. Any other questions before I move on? Yeah.
How do you ensure that you just back up the primary? How do you ensure you just back up the primary? It can fail over.
Yes, so this is designed that you can do either a switchover or a failover operation to one of the standby nodes. And depending on how you configure it, you can actually choose which standby that you're going to pick to fail over to. And that's the role of the cluster management software like Rep Manager that allows you to define how that's going to happen. With the synchronous replication option, you can specify which servers that you would like replies from, and there's quite complex mechanics that allow you to say, I want K replies from this list of servers, so you could get 2 out of 5 replies, that kind of thing. There's different ways of specifying how you get the synchronous replication. We've also got quite complex replication lag management that allows you to tell exactly what the replication latency is between any 2 nodes in the configuration.
Are there any tools to find out the lag?
That's built into the server, so you can actually ask a dynamic view on the master or on any particular node. It will show you what the downstream replication is from that specific node. So you can actually ask it in terms of, you can find out the amount of data that needs to be applied and the estimated lag of that replicated data stream. Anything else before we continue? Okay. So moving on then, we're going to talk about remote data access. These features could in some ways be used for high availability, but they're not. They're really intended for wider application availability. So the best thing to do is to show you a diagram, and the blue blobs are intended to be Postgres databases, and the other colored blobs will, some other database. Could be Oracle, MySQL, whatever. And the arrows are intended to show that you can do both pull and push based data access from the different nodes. So if I start by describing how we would do pull data access, this, if you're used to Oracle, would be just simple remote data access. So first of all, we would create an extension called Postgres FTW. This dynamically loads a new capability into the server, and then we would create a server using the foreign data server command. So I'm creating here a server called red using the foreign data wrapper Postgres FTW, and then providing it some options. And then we're using the SQL standard command for import foreign schema. And what that's going to do is copy all of the table definitions from that remote server and bring them back to the local server. So if you've got 200 tables on that remote server, it will copy all of those 200 tables all into a particular schema on your server. Now, it doesn't copy the data, it copies the metadata, okay? So what we now have is a proxy object called a foreign table that behaves in most ways like a normal data table. The only difference is that when you execute a query like the one at the bottom, against that foreign table, it will go and get the data from the remote server, okay? So it's a proxy object, not a real physical object. So it's a metadata-only object, okay? And what that allows us to do is send data requests in the form of SQL through to remote servers. Now, it doesn't actually need to be SQL, but what we do is we have a mechanism where we provide the where clause and various other components of the query, and that can be translated in a module called the foreign data wrapper, and it can be translated into other SQL. So the Postgres distribution provides something called Postgres FTW, which allows you to access other Postgres servers, and we also provide something that allows you to access files. External projects allow you to access Oracle, MySQL, or just generic ODBC access. So these mechanisms are intelligent in that we are pushing down the where clause and the column list, and in some cases joins down to the foreign server. So if you join two tables together, it doesn't always bring the whole table back to the local server and then do the join. That would be pretty stupid, right? So we've gone to a lot of trouble not to do that. But this mechanism allows you to join remote data objects no matter where they are. So if you've got a table on Oracle and a table on MySQL, you could use Postgres to actually do a join between those, and that would be done in an intelligent way by passing down the where clause to each of those data sources before bringing the data back and doing the join locally. Okay, so it's a very good way of doing remote data access in a heterogeneous environment. Now that was pull. We also support data push technologies, and this is a feature that can be described as publish and subscribe replication, but it's also known as logical replication. And this is the form of replication that's similar in many ways to MySQL in that we only pass the data changes themselves. We don't pass things like changes to individual indexes, maintenance commands, that kind of thing. So in order to use this, you would create a publication on one node, and then you would add tables to that publication. So you might have tables X, Y, and Z on that publication. And then somebody else from a different node can create a subscription that reads data from that publication and then places the data changes from that publication into local tables. Now, at this time, you actually have to do the data copying yourself in terms of creating the DDL. Now that sounds like a problem, but obviously if you use the technology I just showed you before for import foreign schema, it's fairly clear that you can copy that DDL across quite simply and easily, okay? Now once you've set up a publish and subscribe, it will stream the data changes from one server to the other, again in real time, allowing you to pass the data on from the main production database through to subsidiary applications within your enterprise. That allows you to do things like a roll-up replication, where you're accumulating data from a number of edge servers, but it also allows you to publish reference data from a single managed reference data source out to a number of other servers. So there's quite a few different use cases that we support with this technology. So for these styles of access, we support both push and pull access to remote servers. The idea is here that we're able to not just provide high availability, but if I can just flip back to that diagram here, what we're after creating is an intelligent network of databases within your enterprise. Not just Postgres to Postgres to Postgres, but actually passing data to and from other databases. And what this allows us to do is allows us to integrate PostgreSQL within a larger enterprise that consists of various databases, some of which we might want to replace, but realistically we know that replacing existing systems takes a long time, and so the only realistic strategy is interoperability, not trying to paint everything the same colour. Do I have some questions on that? There were quite a few good ones on physical, so I hope you're going to test me on these technologies as well. Yep, go.
Are there any data type limitations when you do this?
Not specifically, only that you have to have the data type on both servers, otherwise it would simply fail because you wouldn't know what to do with the data type.
There is binary log, so would that be equivalent to binary log in MySQL?
Yeah, I mean, so the format that we use is version agnostic, and it allows us to upgrade the version as we go as well. So we've spent quite a lot of time thinking about the way that should be done. But the way that data types are stored in Postgres anyway is that it's basically a blob of binary data that has meaning to the data type functions. So what the data that we pass down the wire isn't, it doesn't relate, it's not hard-coded to any particular data type. What you may not know is that everything in Postgres is data type agnostic, and the data type layer is essentially a sort of semantic layer on top of the storage mechanism. So it doesn't actually matter what the data types are. So we don't have any kind of weird restrictions on, varchar 32K or clobs and blobs and flobs or whatever they're called. Yeah. So another question at the back? It depends. At the current time, the integrated version in the server is asynchronous, but there are options that the way that we've designed it is actually quite complex. The send side is built into the server, but the receive side can actually take a plugin. And so what I've showed you as publish and subscribe replication is something that we can extend. There's also some additional tools that you could get, like PG Logical and BDR, that allow you to extend that concept to support wider types of replication. Did that answer your question? It does, yes. So the difference between physical and logical replication is mainly about the content of the data that's sent down the wire. The actual plumbing that we use to send the data is almost identical between physical and logical replication. So the concepts of using a WAL sender and using replication slots and other such things work very similarly between physical and logical replication. We've also designed the server in a way that, now because of that similarity of the plumbing, that's why it's an easy answer to say, yes, we can support synchronous replication as well as asynchronous replication very easily on the server. But many of the tools work in a similar way. Replication lag tracking, for example, is almost identical between physical and logical. And the way that we work means that you can have multiple logical replications as well as multiple physical replications all working concurrently on the server. And concurrently, by that I mean having multiple processes doing the sending and receiving of data. So it's all concurrent. Was that another question? Gosh, I'm probably going almost too quickly now. So I was expecting much more abuse than this. So you guys are giving me an easy ride after your good lunch. So just to sort of finish up talking about the advanced features there, the pull data access allows you to do multi-server heterogeneous queries, and it is designed to push down a lot of the capabilities or the properties of a query directly into the SQL that's pushed down to the remote servers. There are improvements in every release and various details of how that goes, but this is something that provides the types of distributed database queries that we originally saw in Ingres and Sybase, and also the type of replication that we can see in SQL Server in some regards. So, so far I've described two distinct groupings of functionality. The first one is replication for high availability. The next lot of features are about interoperability between servers, both push and pull. And now I'd like to move on to a third category of architecture, which is architectures for multi-node clusters and various purposes that we might use those clusters for. So, multi-node access. So I'm going to start by talking about sharding, and then I'm going to talk some more about the details and problems associated with multi-node query, and then move on to talking about multi-master database as well. So a lot of the features in this section aren't built directly yet into core Postgres, though we have been working putting them in for quite some time. What may not be completely apparent from some of this is that if it takes 8 years to develop a feature, the 8th year is when you perceive that work has happened, okay? So in a lot of cases, it has actually taken 8 years to work on something, and we've been pushing the infrastructure into Postgres, and then in the 8th year, you sort of go, oh, blimey, where did that come from? Well, it's been coming for a long time, but it's sort of building slowly as we assemble the infrastructure components within the server, and that's really what we're doing. So let's talk about sharding. So the concept with sharding is we store data across multiple nodes in a cluster. Now, forgive me if that's very simplistic. After dinner, you're thinking, God, is this guy going to get more complex than that? Yes, I am. What I'm trying to do here is sort of break things down into the actual individual aspects of the feature. So if you, in its simplest form, if you take a database and you just chop it up into pieces and lay them out on different nodes, you can go, bang, I've got sharded database. Well, not really, because it's more complex than that, right? So you need an access mechanism that allows you to determine where the data is. Ideally, we don't want to have to search through every single node to find one row. We want to know ahead of time which node that row is on so that we can navigate directly to it. So you need to lay your data out using some mechanism. And ideally, you would like the scalability of that system to work easily and even better elastically, so that you can enlarge a particular cluster. Now, what we've been putting into Postgres so far is based around the foreign data wrapper technology that I've shown you earlier in this presentation. What people are hoping to do is to use a combination of declarative partitioning and foreign data wrapper technology to allow you to declare a table that is spread across multiple nodes using, for example, a hash partitioning scheme. So if you imagine that you've got 4 nodes and you're going to create a partition that consists of slices of the table on each of those 4 nodes using a hash partition, you can then navigate to that data fairly easily. Now, as at Postgres 11, which is due out in September, we will have achieved basic sharding using those natural capabilities in Postgres. But I will be the first to say it isn't meant to be full all-singing, all-dancing clustering. This is just a technique for sharding. So the very simplest, the first rung on the layer of distributed systems. And that's what we have built into Postgres 11. Having said that, there are a number of other technologies already existing that provide that for the Postgres environment. They're just not built fully into Postgres core yet. So some of the problems that we're going to face in the future and that other systems already solve are the issues of multi-node query. Because if you want to run a query against multiple nodes at the same time, you need to have a consistency model that makes sure that you return the correct answer even under concurrent data loads. You also need at some point to have a node redistribution technique that allows you to join tables that are distributed differently across the nodes, specifically to handle join types, and obviously a multi-node aware optimizer. So Postgres core does not yet have that, and some other systems do. An example of that is technology for massively parallel processing using PostgreSQL syntax. And the layout of some of these systems is strikingly similar. This is a diagram of PostgreSQL, but this very same architecture was originally deployed by Teradata about 30 years ago and is now copied by things like Redshift, Greenplum, and various other technologies. Okay, so this idea of a statically defined architecture is a very common design pattern. So if I explain how that works with the software called PostgreSQL, PostgreSQL is a fork of Postgres 10 designed to provide scalable PostgreSQL so that it performs multi-node parallel queries. The tables are hash distributed across the architecture, and you've also got an option for replicated tables, which are appropriate for small reference tables. The architecture also supports multi-node transactions, which is obviously useful when you're doing things more than just simple single transaction data nodes. And it also has a mechanism to provide multi-node consistency for those multi-node queries, as well as an optimizer that can handle planning of multi-node queries. So it includes a number of different features that are not yet available in Postgres core and won't be for some time. And that's why you see work being done outside of Postgres core to support these additional MPP capabilities. Now, surprisingly, the only project that does this that has the same open source license as PostgreSQL is PostgreSQL. Greenplum does have an open source license, but they're not compatible, and many of the other systems are not open source at all, leading to this quite a few different ways of accessing your data and many commercial interests there. But we are trying to move forward in this area to put things into Postgres core. There's also another aspect to distributed systems, and that's multi-master access between different databases. And what I'd like to talk about next is the use case that we have for a multi-master database. So if you imagine that we have two databases, one on the East Coast and one on the West Coast, then you'll be familiar with the idea that the ping time between East and West Coast is roughly 160 milliseconds. So if you've got an application server on the East Coast and it's accessing a database on the West Coast, then the time for that write is going to be really significantly different. So the latency of that request is significantly higher than if it were making a write to a local database. So we might expect something like 5 milliseconds for a write on sort of an internal region query, whereas a cross-region query is going to take significantly higher time. Now, I'm not saying that writes on Postgres take 5 milliseconds. I'm suggesting that the total round trip might be 5 milliseconds. In a lot of cases, we'll see single requests on Postgres being 100 nanoseconds or that kind of region on the right hardware. So that gives you a significant latency problem between servers. Now, if you want to do reads, that's easy, okay? We've solved distributed reads many years ago. Distributed writes, a much more challenging problem. So the solution to that is a technology called Postgres BDR, and in that technology, we actually have full write masters laid out across different regions. And in that particular architecture, you're able to do your database writes directly to your local database master, and then those changes are passed across to the other nodes. Now, some people at this point ask me, are those changes passed asynchronously, or is it done in a consistent way across nodes? And what I can say is in BDR3, both ways of access are possible. So according to something called the PAC-ELK theorem, you have to choose between good latency or good consistency, and BDR gives you both choices. So it's up to you to choose whether you want to get a fast write to your local node followed by asynchronous propagation of those changes, or whether you wait for consistency across multiple distributed nodes, which can take up to 3 round trips to all of those nodes. So you've got a choice between 5 milliseconds or 500 milliseconds is a typical choice, okay? And guess which choice people make in the real world. Thank you. Lady gives me 10. Yep.
So, I was sitting through the Postgres tutorials on Monday.
Yep.
And I kept hearing people say, is that BDR? Is BDR built into core Postgres? Is it an open source plugin?
Yeah, so...
It's been around for a while, but the multi-master seems to be the thing that, quote unquote, is missing, but...
Sure. So we've been building, Second Quadrant has been building BDR since fall 2011. So at this point, it's been a seriously long haul, which is no bad thing. So the majority of BDR is now built into core Postgres. The recent BDR3 announcement that we made last week is for a BDR plugin that will work on top of core Postgres, but that plugin is at this time not open source.
So is the core Postgres going to catch up with that BDR3, or are you guys going to diverge? Or?
No, there's not going to be any forking at all. I mean, I'm one of the core committers, so what we find is that the pace of development of things in core is just simply slightly slower and behind the pace of solution development outside. So basically, there's a very long queue of changes to be made into core, and it does take some years to catch up. So, for many, many years now, we've been committed to making those changes in. I did actually have an infographic that showed how many things have made it into core from that project, and it's quite a lot. So this time it's something in the region of about 75% of the code is now in core, and that's actually the basis for the publish and subscribe technology that I described to you earlier is all submitted to Postgres core by second quadrant. So.
So you know that in terms of robustness, scalability, the BDR3 is probably a little farther ahead than what's in core?
Absolutely, yeah. I mean, the BDR3 technology we're describing as very high availability rather than just high availability because of the nature of the multi-master allows you to use it for what we'd call always-on type systems. And the characteristics of those is really almost zero downtime, simply because switchover does not take any time at all. You just switch from one node to the other. And as a result, we, because of the way the logical replication works, we can do online major upgrades, that kind of thing. So there's really very few causes of downtime in this type of system. So.
So how's the adoption for BDR? Well, it just came out, BDR3 not too long ago.
Yeah, I mean, BDR1 went into production use 4 years ago. We've got quite a few people using that. BDR2 was released last year, which we regarded as a sort of interim step on the way to the full new architecture. And BDR3 is the kind of the shiny new architecture of all of the things that we learned in the last 4 years of using it in production. So there's quite a few different changes in the way that the actual underlying architecture work, really primarily around availability and performance. Yeah, I mean, very sort of re-architecting of the code along the way as well.
On Monday, they were saying that the quote-unquote logical replication that came out was based on PG logical, the whole pub sub thing. And are you guys pulling a little bit of that in the BDR along that you just mentioned earlier?
Yeah, gosh. Well, I mean, it is complex. So what we've been doing is we originally submitted PG logical. That was rejected, so we had to rewrite it as the pub sub technology that's now in core. But PG logical did more than the things that were in core. So PG logical still exists as a useful, almost essential tool for online upgrades. And BDR now builds upon that by releasing a new version of PG logical with extended features. So these things are all sort of like branches of the technology as it evolves. What, from normal Postgres to this, or? So this, yeah, so the Postgres BDR is an extension on top of core Postgres. So if you install the extension onto core Postgres, you would then use the BDR functionality to add a new node, and yes, so no downtime.
So is this synchronous replication with some type of management? Is that what this is?
It can be synchronous in parts. In terms of the full architecture, here I've got, in the diagram, I've got 4 interacting nodes, but in the full architecture, each logical node could be protected by 1 or 2 or more physical replicated standbys as well, giving you a very complex architecture that's very resilient. The main, yeah, we support an unlimited number, but we use one process for each interconnect. So beyond about 50 masters, you're starting to use quite a few resources. So that's not something we're looking to change anytime soon. But well, in practical terms, we don't have any production cases with that many out there. I mean, you know, not that people needed it, basically. So I say this technology is in production use in a lot of cases, in a lot of industries. One public example is actually with a company called Animal Logic, who are the people that produced the Lego Batman movie, and they use that to do film production. I don't think I need to go into any more detail than that, but obviously for some of these computer animated systems, there's a hell of a lot of data that needs to be shared. Exactly, yeah. So it's a really good technology to have the various studios that are part of that group work together. Exactly, yeah. That's exactly how they use it. So, and it works very well. So they agreed to produce a use case. But we've got order entry systems, telecommunications. It's gone. Good. One of the other features that we built into Postgres BDR is actually a form of sharding, because you can define some tables as being replicated and some tables as being stored on the local node. Now this is very useful for a sort of Internet of Things type sharding, whereas instead of building a cluster where you've got multiple nodes in one place, you actually spread the nodes out across the whole world. So you can bring in your Brazilian customers into a node in Brazil, your American customers in a node in America, European customers come into a node in Europe. And you can actually use that as what I'm calling a geographical sharding. Geographical not meaning with GIS data in it, I'm meaning physically separated nodes, yet all working together as part of a sharded cluster.
So you're saying the master itself is a shard?
Yes. Yeah, it could be. I mean, also in this, it's depending on what type of, you basically set the metadata on a particular table to say whether it's replicated or not, which allows you to utilize this capability. So BDR3 runs as an extension on top of Postgres, so it's not a fork of Postgres, it's just simply a tool that you plug into Postgres to make all of this magic happen. We use it for a combination of use cases, multi-master replication, as well as very high availability architectures. The name BDR comes from bidirectional replication, and it's quite literally 2 logical links, one in either direction, plus some complex mechanics for conflict detection and resolution. You've got the ability to specify duplicate and local tables, or duplicated and local tables. And with local tables, you can achieve right scaling. So just in summary of this part, I can say that these techniques I've covered in the last half of the presentation. We have just a swathe of different options, commercial offerings, and differences of opinion even about how some of these things should work. But I've tried to list them up there. We are pushing these technologies into core Postgres. So while these things are available now as commercial forks or commercial things, they will be available in the future within Postgres core. So there's quite a few people working on pushing things into core. So what I've tried to do in this talk is show you the range of different features that are available with Postgres. First of all, I talked about replication for high availability. Then I showed to you some of the features available for interoperability between multiple Postgres nodes and other types of database. And to end with, I've tried to show you a number of different possibilities for how to make Postgres nodes work together in a single large cluster to address a number of different use cases. So I hope that's been useful to you. I've been asked by the organisers to ask you to rate my session, and hopefully they'll tell me what you guys said as well. If you've got any other questions, I'm quite happy to talk to you afterwards. Very happy to get any feedback that you'd care to give.
So for the bidirectional replication you're talking about, is that introducing epoch and then comparing epochs, or how do you do it?
Epochs, you mean for the time wraps? It's not based around the specific XIDs. What we do is use time stamps on the commit records to make that happen. Okay, sorry. I thought you were referring to the XID epochs. So. Okay, so I've been Simon Riggs of Second Quadrant. Thank you for your time and attention, and please enjoy the rest of the conference. Thank you very much.